Hey, this is Stargut, and we're back with a video on binary tree pruning. So in this problem, we're given a tree, and we want to remove the subtrees that consist of all zeros. So you can think of a tree as similar to a family tree. Perhaps this is your grandpa, and your grandpa had one child, your mom, and your mom made you and your sister, right? Or you could have a bigger family. Anyway, the point is each node may have left or right children, or it may have no children. See this leaf node? Maybe this is you and you don't have any children yet. Okay. So anyway, we want to remove the subtrees that consist of all zeros. So maybe your part of your family is like outcast and you want to cut relations with them. Just kidding. Okay, so let's jump into my variation of this. Instead of ones and zeros, we're going to use flies and no flies. So imagine you're a chef and you work at a very let's say it's not very hygienic restaurant, and you often find flies in your soup. So you don't want to serve those soups to your customers. So you only remove, or so when you remove a subtree, you are you're serving it to your customers. You can think of it that way. So you won't only want to remove the soups without flies. So this would be our zeros, right? The flies without soups, and the ones would be the flies. You can kind of see the one in there, right? Those are its wings. Okay, so in order to solve this problem, we need to look up every value in the tree. A common way to do this is called DFS, which stands for depth first search. So this is a common search algorithm you should know that is very useful for searching the nodes in a tree. So the way it works is it goes deep first. So it would go like deep first before searching the rest of the tree. So let me draw up some pseudocode for depth first search. So we're going to call this function serve soup. And what are we going to pass in as an argument to this function? Well, we're going to start out with the root element. That way we are going to be able to search all the soups underneath it. Okay, in depth first search, we want to go deep first, right? So we're going to do a recursive call. So recursive means we are calling, the function is calling itself. So we're going to call itself, and we're going to go deep first. So we're going to go pass in its left soup first. So let's go through this. Imagine this is all we had, right? We're going to go left, and then it's going to be passed in the left element, this one. And then we're going to pass in the left child of this one, and this is going to pass in its left child, which it doesn't have any, right? So we need a termination condition here, which basically means when we don't find a soup, we want to terminate. So a common way to do that is to check if the element is equal to null. Now, when this happens, what are we going to return? So in this case, our function should return a boolean. A boolean is true or false. So we want to return true when a node is found to have no flies, or in the original problem, if it's 0, right? Now what happens when the node is null? Well, we're also going to return 0. In this case, we're going to return that it has no flies, because it would be the leaf node. Only the leaf node or would have no children, right? So let's look at the leaf node. So we return no flies from the left child, no flies from the right child. So the only thing we need to consider whether to remove it or not is whether the node itself has flies or not. Okay, so we've searched all the left children, right? And we have a termination condition right here. So when we terminate, we return true. We are backtracking. So let's say we reached we attempt to go left here. We find out there's no more soup left. We return true. When we return, we're going to backtrack to the function that called this one, right? So basically we're going one step back, and then so we're gonna go right here, right? Because this is the function is basically calling itself, so we're going to return to the earlier state of this function. So we're going to go here. So when we're at here, we finished our job of checking the left nodes for the no flies, but we haven't checked the right nodes yet. So we want to add another line that does that. Okay. So we're just going to do another recursive call, but this time we pass in the right subtree. Okay. Okay, so remember, we are returning true in the case it's null. So remember that true means the soup is good. Okay. We also want to save the value returned by this function, right? So if we go left and we return true, it's going to come back here, but we lost the value of true since we're not storing it. So we want to save that. So let's create a variable called is left good soup. Sorry, my English is not very good. I should say is left soup good. Good. And we're going to do the same thing with the right subtree. Ay, need more canvas. There we go. Okay, so we have the termination condition, but we are still missing the condition to judge whether a subtree, for example this and its left and right children, should be judged as a good soup, right? So how do we do that? So let's look at this node right here. If all of its left children are good soups and all of its right children are good soups and itself is a good soup, then we are going to say, yes, this subtree contains all good soups and we should give it to our customers. So let's put that in pseudocode. If is left soup good. Sorry, I'm recycling these names. I'm going to call this left soup is good just to make it more clear that if it's true, then the left soup is good. So if left soup is good and right soup is good, then what do? Well, we're going to return true. Okay. So, actually, I'm missing something. I hope you caught that. Maybe you caught that. So we didn't check if the node itself is true or not. So we need to check that. And let's see, root. So when is root true? Well, root is true when its value, so root has a property called value, equals no fly. Okay. Okay, so let's perhaps it would be a good exercise to go through an example here. Let's say we are at this node right here. Okay, so we check its left child, it's null, so we return true. Okay, we check its right child and it's null, so we return true. And after we check its right child, because it's null, we return true and backtrack. So now we are here. So basically this, when we return here, this corresponds to this line of code. So we check if its left soup is good. So remember, we return true. So left soup is good contains true. Right soup is good. So that one we also, because it was null, we return true. And root.val equals no fly. So root is this one, and we check the val property, and we can see that there is no fly. So this is what we return here. Okay. Okay. So we also need to return something if the above of this condition doesn't hold. So we're going to say else return false. So that means either it has a fly, the root has a fly, its left children have a fly, or its right children have a fly. Okay, so basically this covers most of the problem. When we are done with the problem, we are going to... Oh, actually, I forgot to cover the most important part of the problem, which is we need to remove the root if it is true, right? Or if it has no flies in it. So we're going to say okay. So this is we're going to do this when we backtrack. Okay. So if this one's left child, the subtree returns true, that means there's no soup found in it. So we're going to set this what do you call this? Its pointer to that subtree to null. So that will essentially cut off the left subtree from this, so that when we return root as our answer, the tree is no longer going to contain this left subtree. So let's add that line of code in here. Okay. So if we find that the root's left subtree is true, we are going to set it equal to null, which is the pruning part of this problem. And we're going to do the same thing with its right subtree as well. Okay, so you can see better here is the pseudocode. Okay, root.left equals null, root.right equals null. Okay, so essentially, yeah, this is the entire problem. Now there is one special case where this having this function alone is going to return the incorrect answer, and that case is when we are given a tree with a single excuse me, we're given a tree with a single element that returns true, right? So imagine you're given this tree, and what we should return is null, because the node itself is clearly has no flies in it, right? So our answer is going to be null because we're removing itself. But if we pass this into root right here, if we can do this, if we pass this into root, it's only going to check the left children and right children of this node, and because those are both true, and itself is true, right, we're going to return true to the function that calls this. So, but there is no parent node, no node above it, that's going to set its left child to null. So our answer is still going to be this. So just to make it clear, let me take you to my LeetCode. Okay, so you see this prune nodes is basically what I've shown you on the paint application, and we're calling this function from here. So this is like our entry point of the solution, right? This is how things get started. So we call this here, and this is the recursive function. And remember that the root node itself may return true if it consists of itself and it's true, or if itself is true and its left and right children are true. So we need an additional condition to see if the root is true, and if it is, we are going to return null. Otherwise, we're going to return the tree without the subtrees that contain all zeros. Okay, sorry if that kind of dragged on a bit, but I hope this makes it clear for you guys how to solve this problem. Yeah. Okay, hope you enjoyed this video, and let me know if you want me to do any other LeetCode problems. Okay, thanks. Bye.